right, ladies and gentlemen, before we get started, the official business, this program will be recorded, not only for us to enjoy, but it will also then be posted to YouTube so that other people who could not join us tonight will be able to watch it. So by continuing on, you are agreeing to be recorded. Let's see here. During the course of our presentation, if you have any questions, you're welcome to ask them in the chat. We may or may not interrupt our speaker at that time, or we'll just hold questions till the end. Depends on how critical the question is. My name is Chris McCall. I'm director of the CERN and Earth and Space Center. I guess I should turn on my camera, shouldn't I? That would be nice. Anyway, I'm director of the CERN and Earth and Space Center here at Triton College. There are 2 planetariums in Chicago. We're the one with free parking. Everybody laughs at the old joke, but anyway.
It's true. It's true. Especially if there's a game.
Yes, yes. So we're open to the public. Right now, just Saturday nights, but our attendance is increasing steadily. We're still doing school shows, virtual field trips, private events and parties, working with a wide range of Triton College professors, including electronic music and photography, are 2 new disciplines this semester. So just lots of stuff going on here. And they're hopefully with the help of CAS, the Chicago Astronomical Society, we will be able to set up our first public observing session likely after the first of the year. So come on out and enjoy us. Anyway, you can visit our website, triton.edu/CERN. We're also on Facebook. We also have a YouTube channel. And if you have any questions or comments, let us know. And I think what I'm going to do is go ahead and turn this over to Jim Kuka and let him set it up for CAS.
All right, thanks, Chris. Welcome, everybody, to the December 2021 meeting of the Chicago Astronomical Society. Our speaker tonight is Kevin Cole. Kevin is assistant professor of astronomy and geology at Harper College. Tonight, he is going to cover 2 main topics dealing with asteroids. The Lucy mission, which just launched, is on its way to the Trojan asteroids that flank Jupiter on both sides. And the other topic, the one that has gotten a lot of media attention lately, is the double asteroid redirection test, which will involve the idea of diverting an asteroid before it strikes the Earth by what is known as kinetic impact. It's very interesting because it's a method of potentially protecting the Earth from a devastating asteroid impact. So without further ado, Kevin, the meeting is yours.
Okay, thanks, Jim. Okay, good evening, everybody. So I'm going to share my screen here. I think I'm going to stop my video so it doesn't get distracting to anybody, especially me. So let's go ahead and share. Okay. Everybody see the screen okay?
I see your slides, Kevin.
Okay, good. All right. So let's get started here. Okay, so again, my talk today is going to be on 2 very ambitious asteroid missions, and we're getting better and better at visiting asteroids, especially those that happen to cross our path, but even more ambitious ones that we've never seen before, and those are the Trojans. So when we take a look at the solar system, we take a look at a what appears to be quiet, but it really isn't so quiet. Earth is pretty much hit with debris all the time, on the order of about 5,000 tons of debris fall into our planet's atmosphere and burn up in the atmosphere. And quite often you could see them in the form of these streaks of light that we call meteors. And sometimes we wind up getting a whole shower of meteors coming in as a result of the debris trail left behind by a comet. And these are the meteor showers that are 13 or 14 or so meteor showers per year. Some of the major ones, there might be some minor ones in there as well. And an interesting little factoid that you may or may not be aware of, some of these little tiny bits of dust and sand grain sized material has metals in it, like iron. And this material just doesn't vaporize in the atmosphere. It actually settles down into the atmosphere and eventually can get incorporated into rain and snow. So if you have a nice strong magnet, you go up to your gutter after a rain or even at any time, and you run your magnet over the gutter, close to the bottom of the gutter, you might pick up some metal fragments. If you do, those are probably pieces of metal from space, from these cometary debris that's burning up in our atmosphere. Every once in a while, we'll get a piece of debris that can actually make it down to the surface. These are called meteorites. Here's one example, and this is the Gibeon meteorite. This was on display at Arizona State University, and this is solid iron and nickel. And it's suspected that this comes from the core of a processed planet like our own that's got an iron core, a mantle, and a crust. So there's about 60,000 of these in collections around the world. And typically they're not going to have too much of an impact because a lot of times as meteors hit the atmosphere, they'll break up and fall smaller pieces. But what happens when a larger object makes it through the atmosphere? Maybe the one the size of a football field. Well, you'll get something like this. This is Meteor Crater in Arizona. And this is about 1,200 meters across, 200 meters deep. And the impactor that created this was about 100 to 150 meters in diameter, somewhere around there. And this was actually made by the same type of meteor as the Gibeon. It was an iron meteorite that struck the surface and created a big hole like this. To give you an idea how much energy was released, this had an explosive yield of some 20 megatons. And that's enough to flatten any city. Even though the impactor left a crater only about 1,200 meters across, the shock wave would have been far more extensive. And to give you a better appreciation of how long ago this is the second youngest meteor crater on the Earth. When this hit in the southwestern United States, there were no human ancestors around. They hadn't migrated over from Asia yet. And the only thing to see this impact hit were probably a few coyotes and roadrunners swimming around. So this is the kind of question we want to answer. If something like this comes in our direction, what can we do about it, if anything? Are we reduced to calling up Bruce Willis and his team of oil riggers to send on a space shuttle to blow up the asteroid in the nick of time? Or is there something a bit more practical that we can do? So this leads us to the DART mission. And as Jim said, DART means Double Asteroid Redirection Test. And this is called Double Asteroid because we are going to be visiting a double asteroid, a large one called Didymos and a smaller one called Dimorphos. And Dimorphos is going to be our target. So just to get it started out right, let me get this little green guy out of the way right there. And I'll put it down here. That should be good and out of the way. The SpaceX Falcon 9 rocket blasted off successfully from Vandenberg Air Force Base at 10:21 Pacific time, 12:21 Chicago time on November 23rd. And it was, I didn't stay up to see it, but I saw the replay, and it was any night launch is a spectacular launch. And the target is going to be Didymos, which means ancient traveler, and Dimorphos, which means mighty moon. So this is going to be a test of a technique to divert an asteroid if it's coming on a collision course with Earth. And here's a view of the spacecraft. I'll show you a bit more of the spacecraft in a little bit. I'm going to minimize that. Okay. Oops. Come on. There we go. So what is this concept of planetary defense? Well, this is something relatively new, but NASA's been studying it for quite a long time. Basically, we want to see what we can do to mitigate any kind of potential asteroid collision with our planet. Most of the asteroids that cross our planet's orbit are very small, typically we can't see them until we actually image them with our telescopes. Once we image them, then we can figure out what their pathway is. But basically, it consists of search, detect, and track, then characterize what kind of rock are we taking a look at. And we have several different types of spacecraft and surface instruments to do that, including NEOWISE, which is an infrared spectrometer, the Goldstone radio telescopes, and the infrared telescope facility. Plan and coordinate, and mitigate, and then finally assess. So if we take a look at the steps that NASA has established as their Planetary Defense Coordination Office in 2016, this office is designed to provide early detection of potentially hazardous objects, or PHOs. NASA sure loves its acronyms. The subset of NEOs whose orbits predict that they will come within 5 million miles of Earth's orbit. And a NEO is a near-Earth object. There are 3 types of near-Earth objects. These are Apollos, Aitons, and Amor asteroids. And these are asteroids whose orbits cross our own orbit or skims the orbit very, very closely. And these are the ones we have to take a close look at. So of those, a large number of them, between 30 and 50 meters, can cause significant damage on Earth. Now, one thing to recognize too, that our planet is 75% water. So chances are it's going to hit the surface of the ocean before it hits New York City or Chicago or anything like that, despite what the movies say. But on occasion, something like this could wind up falling over a large city, like it did back in 2003 over Park Forest, Illinois, and like it did back in, I think, I don't know, what was it, about 2013 in Chelyabinsk, Russia. But those are pretty rare. But at any rate, basically what the Planetary Defense Coordination Office also wants to do is track and characterize these PHOs and see what their orbits are going to be like. And is it possible that these objects could pose a hazard to the planet in some way or another? So in order to mitigate this, many studies, strategies, and technologies are being investigated to see which is going to be the best technique to divert these objects. And this is all going to start playing a role in coordinating U.S. government planning for response to such an actual threat. And this is important because this could be even more devastating than a terrorist attack, for example, because it could really be something that you see coming potentially, but can't do anything about it. So we're going to try to do something about it with this test mission. So if we take a look at the number of near-Earth asteroids that we can encounter, we have a population density that looks like this. The brown colored asteroids are known asteroids. The green ones are those that are predicted through the Wide Field Infrared Spectroscopic Explorer. I'm not sure if I got that acronym right, but it's close enough. And the blue is the predicted total as established before the WISE spacecraft was launched. So we see here that with each of these representing 100 objects, so objects that are in excess of a kilometer in diameter, we have 2, 4, 6, 8, 10, maybe about 10,000, or should say about 1,000 of these to be aware of. As they get smaller, you can see the number get larger and larger. So between 500 and 1,000, that number probably more than doubles. Between 300 and 500 meters, about triples. Then we get to 100 and 300 meters. You can see it gets even larger still. And less than 100 meters, it could be countless. So typically what we're going to be really more concerned about, not so much the big guys, because these are actually fairly easy to spot, and there are not that many of them. But the smaller ones are the ones that can be of concern. And even a small 100-meter size rock can sometimes, if it's made out of the right material, can make it through the atmosphere without breaking apart. So a solid iron meteor can actually make its way through the atmosphere and hit the surface with a fairly devastating impact. So to give you an idea, the size of a crater you might get, typically the size of the crater is going to be about 10 times the size of the diameter of the meteor. So a 100-meter diameter impactor is going to create about a 1 kilometer size crater, more or less. It's a good rule of thumb to kind of work with. So When you get up to this 1 kilometer range, now you're taking a look at a impact crater that might be up to 10 kilometers in size. So all these are going to be of particular concern, but the smaller you get, the easier it will be to divert the asteroid. When you start getting into these bigger asteroids, now you're going to have to start being a little bit more creative. So here's an example of an asteroid that was spotted by the late Arecibo Observatory in Puerto Rico. That's going to be an instrument that's going to be sorely missed, because this radio telescope was the largest radio telescope in the world, and it was designed not only to receive radio signals from space, but also to transmit radio signals into space. There's nothing on the planet right now that can do that. The Chinese telescope that was just built is larger, but it cannot transmit radio energy. So what was done with the Arecibo Observatory is that radar pulse is sent to this asteroid. We can actually paint a picture of the asteroid in radio signals, and that's what this particular asteroid looks like. This is Dimorphos, so we're taking a look at. This is going to be our target asteroid, and that little dot right above it there, that's Dimorphos. That's its little host, a little satellite moon. And we are finding out that a lot of these small asteroids have these even smaller companions along with them. Either they were got there from maybe a previous impact, or maybe they fell into the very small gravitational well of the asteroid and have been there ever since. So to give you an idea what Dimorphos might look like, this is a picture of asteroid Bennu, as taken by the OSIRIS-REx mission. Asteroid Bennu is about 510 meters in diameter. Didymos is about 780 meters in diameter. Now, we really have very little information about what the asteroid looks like other than these radio telescope images. But it may look something like what we see here with Bennu, rather irregularly shaped object. And it looks like basically a rubble pile that's rotating pretty fast. By the way, OSIRIS-REx will be returning to Earth with its sample very shortly, and it should be back by 2023. And it looked like they collected a pretty good sample here. And the Japanese Hayabusa 2 created a sample collection event on the asteroid Ryuju, and Ryuju is about the same size as Didymos, about 710 meters in diameter. And that spacecraft has already returned with its samples. So that would be an interesting subject for a future talk, maybe, as we get more information on it. But anyway, this is the target that we are going to be looking at. So here's the scaling factors here for these asteroids. So we have, here's a bus, your typical bus. Here's the DART spacecraft with its solar array fully deployed. It's about 19 meters in diameter. Statue of Liberty. Here's little Dimorphos. This is our target, 163 meters in diameter. Great Pyramids, Eiffel Tower, World Trade Center, and here's Didymos. It's 780 meters in diameter. So these are the types of asteroids that are the most numerous in the inner solar system, and probably in the solar system in general. But these are the types of asteroids that will be crossing our path. So we're choosing this little guy right here because it is in orbit around Didymos. Okay, for some reason, I get technical problems here. Oh, there we go. Sorry about that. Okay, so this is what the orbit of Didymos looks like. Its orbit takes about 770 days. It's slightly inclined to the ecliptic plane, and you can see that its orbit just skims the Earth's orbit right here and heads out beyond the orbit of Mars. So this is what's going to happen. This is the DART spacecraft on the bottom right here. And along with DART is this little subsatellite called, I think it's pronounced Lycia. I could be wrong on that. Don't quote me. But what we're going to do is we're going to send this on a collision course with the asteroid. And the idea is as the spacecraft is moving, it's got a certain amount of kinetic energy and a certain amount of inertia. And when it hits the asteroid, it's going to transfer that kinetic energy and inertia to Dimorphos, and conceptually, it's going to slow it down in its orbit around Didymos, and it's going to start to get a more elliptical orbit, and this will be the new orbit. So in white here is its original orbit, and this blue orbit is going to be its new orbit. So if this works, we'll get an idea of just how much energy it would take to divert an asteroid about this size off of its current pathway. And to observe this is going to be this Licia cube. Now the spacecraft has a camera on board, and so does Licia. So the camera on board the spacecraft is going to be operational all the way to the point of impact. And then Licia is going to observe the impact, fly past the asteroid to get a close look of it, and maybe get a general look of the asteroid as a whole, and then that'll be it. So this is actually going to be a very quick type of mission. So this is what the spacecraft looks like. It's actually a pretty interesting little spacecraft. You can see right here with the engineers, the small size of it. And it's testing several new technologies, including a rollout solar array. Now, the rollout solar array has already been demonstrated at the space station, and it worked really good. So they are going to be applying it to this mission right now. And the idea here is nice and compact. So when it is ready to deploy, which it should have done already, it'll just roll out nice and easy and simple like that without any chances for getting hung up or anything like that. So this is one bit of new technology. They've also got a new communications array on the side here to help to, I think it's supposed to increase the data rates being sent back by the spacecraft. As I said, there's only one science instrument aboard the spacecraft, and that is a camera that will be observing the asteroid all the way up to the point of impact. And the Licia cube is an acronym for Light Italian CubeSat for imaging of asteroids. And this will deploy just about 10 days prior to the impact. So it'll be able to catch images of the actual impact itself. So that should be quite a sight to see. Again, this is a very low cost spacecraft. The spacecraft goes, and as you can see, it's only about 4 by 4 by 4 feet in size. But even at that, it still needed the Falcon 9 rocket to get it out of Earth's gravitational well. And on top of that, it's going to be demonstrating a new ion propulsion system. This is what they call the Evolutionary Xenon Thruster Commercial, or NEXT-C. And we'll see what the performance of this is. So in effect, this is going to be a proof of concept type of mission to divert the asteroid. Plus, we've got some technology demonstrations aboard the spacecraft as well. So let's take a look and see what this mission is all about in kind of a animated nutshell. So there's deployment. This has already happened now, don't forget. So the solar array was deployed before it got too far away from the Earth. And there it is in its configuration. Then it's going to head on to the asteroid pair. And that camera is going to be operational all the way to the very end. So there's a sub-satellite. Not much bigger than a briefcase. And they'll have fold-out solar arrays. And this little guy right there, that's our target. So this is going to be self-navigating. There's no way you can steer it from Earth. And when it hits, we'll be able to actually see it. And once it hits and the small satellite has ended its mission, then it'll be up to the Earth-based observatories to keep track of the satellite to see how the asteroid's orbital path around its host asteroid is changing. So an extremely challenging type of mission that has never been done before. And if this works out the way we hope it will, may lead to some more ambitious types of redirect type of missions of larger asteroids with newer technologies. And one idea that could be applied for a larger asteroid is to actually send a spacecraft and rendezvous with that asteroid at a distance farthest from the Earth. And the small gravitational well of that spacecraft could actually divert the trajectory of an asteroid enough to make it miss the Earth. So I imagine that they'll try a test like that one of these days. But I'll be happy if this particular one gets off and running as successfully as it has done so far. Okay, so with that said, let's go on to another very ambitious mission, and that is the Lucy mission. This mission successfully launched October 16th. So within about a month of each other, two very ambitious asteroid missions were launched, one from Vandenberg Air Force Base and the other one from Cape Canaveral Space Force Station in Florida. And it launched it on October 16th. And I think this was another early morning hours launch. And it was another spacecraft that was launched aboard a Falcon rocket. The Falcon rocket is proving to be an extremely reliable and capable spacecraft. On top of that, it lands and it could be used again instead of just being tossed away. So this is turning out to be a very important resource for NASA to take advantage of. So this is the launch of the spacecraft on October 16th. The launch went well, except for one problem. Upon deployment of the solar arrays, one solar array didn't lock into place. And engineers are seeing if they can fix that issue. It's not going to affect the spacecraft too much because the array that has it completely locked into place is still supplying 90% of its expected power. And this is the same type of solar array that has been used on other surface missions to Mars, for example, and other Earth orbiting missions. And it folds out like a fan, and it actually compacts very nicely in the spacecraft configuration. So this is a pretty decent size solar array that we're taking a look at here, and it has to be because it's going all the way out to Jupiter. So the solar cell technology has gotten efficient enough now that we can start sending spacecraft out to Jupiter. Before that, we couldn't do this because the sun's light was so weak. The technology wasn't there to collect it, so we had to rely on radioisotope thermoelectric generators. In other words, a radioactive material, a little tiny radioactive battery. But now this is getting better. Juno is using the same type of solar cell array in its orbital mission around Jupiter. And so this is the second mission that's going to be going out to that distance with solar cells. So this is another new technology demonstration that NASA is also incorporating into this mission. So what is this mission and why is it called Lucy? Well, on one hand, for those of you that know anthropology, Lucy was the hominid fossil discovered in 1974 by anthropologist Donald Johanson. And it was considered to be the oldest representation of the hominid family. Our earliest beginnings out of the forests of Africa and into the tall grasslands, if you will. And everything else is basically history, as they say. And this was named after Lucy because this mission is kind of the same thing. We're taking a look at the origins of an important asteroidal family that has never been visited before. And the only thing that we've seen of those asteroids are very faint images in telescope plates. And also it's mentioned that while the engineers were designing and putting this spacecraft together, somebody was listening to the Beatles' Lucy in the Sky with Diamonds and thought, hey, that'd be a pretty good name too. So that's the story about how Lucy got its name. This is one of the few missions that had been launched that actually is not an acronym. It's actually a name. So what are the target asteroids? Well, we have one main belt asteroid, and that, of course, is Donald Johanson. This will be the first asteroid visit. This is a real tiny one. And then we're going to be visiting these asteroids here. The asteroids first we'll visit are those that are in the L4, what are called the L4 Trojans. This will include Eurybates, Polymele, Lucas, and Orus. And then they'll leave that section of the solar system, come back around to this section of the solar system and look at a double asteroid called Patroclus and Minodius. I think I'm pronouncing that right. Hope I am. So what you have to do here is to make use of gravitational assist from the Earth. So here's where the asteroids lie. They're in what's called a Lagrange point, L4 and L5. And this is a gravitational null point that exists between the gravitational field of the sun and the gravitational field of Jupiter. So the objects right here are not falling into Jupiter and they're not falling into the sun. They're just kind of sitting there. And you can see the population is quite extensive. So to see what these are all about is important because we've been visiting main belt asteroids, we've been visiting near Earth asteroids, we've been visiting comets, but these guys we have never visited. So this might provide some important information about the early history of solar system formation, and about the motion of Jupiter itself. Well, many of you may not realize this, but Jupiter was likely the first planet to have evolved, formed in our solar system, and it didn't stay there. It, along with a proto-Saturn, migrated into the inner solar system and then migrated back out again. And as it did so, kind of disrupted all the rocky and icy debris in this region. And some of that might have gotten trapped here in these Lagrange points. So how are we going to get there? Well, launch, as I said, has occurred. Our first flyby is going to be in 2025. That's going to be by the C-type asteroid, Donald Johanson. I'll get into some of these different types of asteroids in a moment here. And then from there, in 2027, we'll fly by your bodies. And then a month later, we'll fly by Palaemale. And then the following year, we'll encounter Lucas. And later on that year in 2028, we'll encounter Orus. Then head back around and cross onto the other side of the solar system, where in 2033, this is a very long mission, as you might expect, it will fly past the binary pair, Patroclus and Minodius. So to do this, what they're going to have to do is, once launched from Earth, it's going to do kind of a roundabout flight around the sun and get a gravitational boost from the Earth to give it enough energy to head out to the outer solar system. And it'll fly through the asteroid belt. And then it's going to come back into the inner solar system, get another gravity boost from the Earth, and head out to the Trojans. And this is why it's going to take so long to go from one side of the solar system to the other, because we got to go through this roundabout manner, because this little spacecraft does not have its own massive propulsion system. It's only got reaction control thrusters to give us a very slight course correction maneuver. So everything is coasting, behaving very nicely with Newton's laws of motion. So this is going to be the pathway that the spacecraft is going to be following in its trajectory towards first L4 and then L5. So what about these classification schemes? Let me go over these really quickly so you don't get too confused, because there's quite a few various types. Most people talk primarily about the carbon-rich asteroids, or the C-type, and the metal-rich asteroids, or the S-type. So basically, the C-type asteroids are represented by this meteorite right here. This is a carbonaceous chondrite called the Murchison meteorite, and it's carbon-rich, and it is suspected to have come from these carbon-rich or C-type asteroids. There are other types of asteroids within this family, the rare B, F, and G types, which are also carbon-rich, and they make up some 75% of known asteroids. They're very dark, as you can see right here, so the reflectivity is very low. So detecting these is very difficult. They've got a reflectivity of only 3%. So only 3% of the sunlight that hits the surface reflects back out into space. So we visited one of these already, and that was Ceres, the largest of the C-type asteroids. And a goal here is to compare these with these meteorites that we have in our collection, see how comparable they are, and what kind of organic compounds, because these C-type asteroids do have organic compounds in them, as do these carbonaceous chondrite meteorites. And this might give us clues as to how life got seeded on our planet, and maybe even Mars and Venus at one point early in the solar system. Those are the C-types. The S-types make up about 15 to 20% of known asteroids, and these are more metal-rich, so they're relatively bright. They have a reflectivity of 10 to 22%. And they are made up of a mixture of nickel and iron magnesium silicates. And an iron magnesium silicate is a mineral that makes up the oceanic basalts that we see here on our own planet. And these are minerals such as olivine and pyroxene, for example. And we see a lot of that in these types of S-type asteroids. So the S-type asteroids are very similar to the stony iron meteorites that we see on the right-hand side here. This is called a palisite, and the ordinary chondrites that we see right here in the middle. And it's suspected that the ordinary chondrites represent the crust of a protoplanetary body, whereas these palisites represent the boundary between the mantle and the core of a protoplanetary body. So we have these brownish colored minerals. Those brownish colored minerals are olivines, and this kind of grayish looking color right here, that's all iron and nickel. So that's pure metal right there. So we have kind of a cross-sectional look. So those make up the S types. M type makes up most of the rest of the asteroid belt. So there's somewhat 5% left. So their albedos are comparable to the S types, 10 to 18%. And these are comprised of nickel iron. Again, similar to the iron meteorite that we see here at the Gibeon. We are going to be visiting a nickel iron meteorite with the Psyche mission that's going to be launching, I think, in late 2022 or early 2023. I forget the date. So we'll get our first look at a iron-rich asteroid, something that's never been seen before. And then there are some more rare ones called the D and P type, and these are at the outer edge of the main belt. And these are basically going to include not only those at the outer edge of the main belt, but the Trojans and some of Jupiter's small moons as well. They tend to be very dark, and they may contain very primitive organic compounds, maybe the basic chemistry, even more basic than the carbonaceous chondrites that could have led to organic chemistry on planets like the Earth, Mars, and Venus at some point in the early history of the solar system. So these are the main types of asteroids that have been visited, and representing some of the meteorites that have been collected to compare them and contrast them. So as we take a look at these Trojans, this is what we know about them so far. Patroclus is about 113 kilometers in size, and it's a P-type. And astronomers are able to get these sizes of these asteroids because they look for what are called stellar occultations. So an object like an asteroid will pass in front of a distant star, and astronomers will time how long it takes that star to appear on the other side of the asteroid. And knowing the distance that the asteroid is from the sun will give them an idea how fast it's moving, and then they can determine what the actual size of the asteroid is. So there's some measurements we can take from Earth very nicely. So we see Patroclus and Minodius are both considered to be P-type asteroids, very close in size to each other. So of course, these are much, much bigger than what the DART mission is going to be visiting. But this kind of gives you an idea of what they look like. Eurobodies is a C-type asteroid, about 64 kilometers in size. Orus, about 51 kilometers, a D-type asteroid. And Lucas, also a D-type asteroid, a little bit smaller. And Polymele, even smaller still, and that is, can't read it right there. Why don't you get out of the way here? That's also a P-type asteroid. So, and then there's little Donald Johansen at 4 kilometers in diameter, and that's a C-type asteroid. So we'll be making our first flyby of Donald Johansen. This is a main belt asteroid. Now, these are pictured here as somewhat spherical, but they may not be. An object will become spherical if its gravitational field is weaker, or I should say is stronger than the material that makes up that object. So typically, you have to have an object in excess of about 300 kilometers or so in order for that to take effect. But, you know, there's always exceptions, and we may find some exceptions here. And undoubtedly, these are going to be asteroids that are heavily cratered, as everything that has a solid surface tends to be, especially in the outer asteroid, in the outer asteroid belt, but also in the outer solar system. It's doing it again on me. Oh, boy. You can tell this is live because we got little glitches here. There we go. So this is what their rotations look like, and it's kind of interesting to see how they rotate. Typically, most objects in the solar system are rotating in a counterclockwise direction. And this goes back to the conservation of angular momentum as the initial formation of the solar system was proceeding. So that's why all the planets have a counterclockwise rotation, and most of the moons that orbit around those planets also have a counterclockwise rotation. So when we see Patroclus and Minodius and Polymele and Donald Johansen and Lucas rotating the way they are, that's kind of expected. However, we see Eurobodies and Orus rotating in the opposite direction, rotating clockwise. So what's going on here? Typically, something like this happens when an asteroid gets hit by another object, maybe almost the same size, and it changes its rotational characteristics. So there could be a lot of reasons for this, but this is what is suspected to be going on here. And the size of the impacts on these asteroids can give us an idea what the composition of these asteroids might be as well. So if you notice on here on Oris, the artist's rendition is a really large impactor, and this is still together. And you would expect a very large impact like this would have blasted this asteroid apart. If this turns out to be the case, and this would tell us that Oris is basically a rubble pile in which there's a lot of void spaces inside, and the seismic energy gets dissipated very quickly and it doesn't break apart the asteroid. If we have more small asteroidal impacts like this, this is telling us that, again, it's probably more of a solid body than it is a rubble pile. But this is just going to have to wait until we get there in middle of the 2020s. So if you're on 2025, then we'll start taking a look at these guys. Now, Patroclus and Minodius are kind of an interesting, not comet, but the asteroidal pair. And the question is, could these be interlopers from the Kuiper belt? Could they be cometary bodies? And that's kind of interesting. They're not close enough to the sun to behave in a cometary manner. Basically, when you get into the inner solar system, you come to a point that's called the frost line, and it's halfway into the asteroid belt. Typically, when the comets start coming into the inner solar system, they'll start becoming active once they cross this frost line, because the temperatures are getting high enough where the ices on the comets are starting to sublimate away and starting to create the coma that comets are so famous for. So typically, they're not going to start becoming available till just before crossing the orbit of Mars. So the question is, could these guys be trapped Kuiper belt objects? And that's one thing that's that astronomers are hoping to observe. So as we can see right here, these two bodies have an orbital period around their common center of gravity of about 4.283 days. Their distance between them is about 680 kilometers, and their orbital inclination is about 22 degrees. So when we take a look at this diagram down here, these shapes are determined by Earth-based occultation measurements. So we got a general idea of what the shapes might look like. And all these parallel lines, you see these dark parallel lines, are observations from single observers, or a single observer. So of course, it's going to take quite a bit of time. Very dedicated observer here, and seeing how these asteroids pass in front of a distant star to get a good size representation. The red lines here indicate that the observer saw the asteroid pass in front of the target star to ascertain the location and shape of the asteroids. And then the blue dashed line that we see here crossing through the center represents the long axis for each object. So we can see the long axis of one object and the long axis of the other object. And of course, they don't quite line up with each other, as you might expect. And here is our best image to date of Patroclus and Minodius, taken by the 10-meter Keck telescope. And that's about as good as we can get. The only thing you can tell about this is a measure of their reflectivity of the surface and maybe any variability of surface brightness. But in a few years, this is going to change. By 2020, no, actually in this case, by 2033, we should get our first good look at these two bodies, and hope that our spacecraft will make it through that long journey. Now, the question is, why does Patroclus and Minodius exist at all? Why is there a binary pair here? And this might lead to a little concept called the Yorp effect. Yorp being named after the scientists who coined it by the name of Yarkovsky, O'Keefe, Radzievsky, and Paddock. And basically, we're taking a look at how light from the sun can warm up an asteroidal surface. And as that heat is radiated off that asteroidal surface, it can start to increase the rotation of a small asteroid, and even can change the orbital characteristics of that asteroid. So I'm going to show a quick video on this, and this is going to be more of a visualization of what this is all about.
From a distance, everything in our solar system appears to be in its place. However, if you take a closer look, sometimes you can find asteroids, like Bennu, leaving their home in the inner asteroid belt and passing very close to Earth. Most other asteroids tend to stay grouped together in a few regions of our solar system, yet some still end up in our backyard. So once these asteroids get close, what makes the difference between a near miss and a potential hit? NASA's OSIRIS-REx mission will help better answer this question when it visits Bennu, but scientists think that a force called the Yarkovsky effect might be an important part of the answer. So how does this effect work? Well, like Earth, most asteroids rotate slowly as they move through space. During the day, the surface of the asteroid is illuminated by the sun, so it absorbs heat and grows warmer. During the night, however, the surface cools down, emitting the heat absorbed as radiation. This radiation exerts a force on the asteroid, acting as a sort of mini thruster that can slowly change the asteroid's direction over time. On larger asteroids, this doesn't amount to much, but on small ones, it can make a pretty large change over time. Because the surface emits the most heat radiation at the end of the day, the direction the asteroid rotates can ultimately determine what happens in the long run. Other factors, such as composition, asteroid shape, and surface features, can modify the magnitude and direction of the Yarkovsky thrust. By studying the Yarkovsky effect on Bennu with the OSIRIS-REx spacecraft, NASA scientists hope to better predict how an asteroid might move through the solar system and whether it poses any danger to us here on Earth. So the next time an asteroid starts gradually moving into our neighborhood, we'll have a better idea of exactly where it'll end up.
So that's a little bit of an introduction on what's called the Yarkovsky effect. And the Yorp effect is basically an extension of that, because now we're taking a look at the rotation rate of a small asteroidal body. And this is something that's not going to happen in a few hours. This is something that'll take tens of millions of years to start to spin up. And if we're taking a look at an asteroid that's primarily a rubble pile, as actually most asteroids are, if it can get up enough rotational energy, centrifugal forces could actually cause the asteroid to start to break off in pieces, and you might have another piece break off and become a satellite of that object. So this is what we call a fission protobinary, and then dynamic processes over less than a year's time wind up getting to a point where these objects could actually escape the very tiny gravitational wells of these asteroids. So it would be interesting to monitor this effect as well among the Trojans, especially these two in the L5 location, to see if this Yorp effect is applicable to Minodius and its cousin, and see if it actually works and how it compares to what was observed at Bennu and even at Ryugu. So before I let you go, I came across a really cool picture of Comet 67P, Churyumov-Gerasimenko. I can't tell you how long it's taken me to learn how to pronounce those names. But anyway, this is an image taken by the Rosetta spacecraft in 2014. And we see this beautiful tall cliff. It's about 1 kilometer in size, kilometer in height. And we see a rubble pile at the bottom here. And these rubble piles are not unusual on the surface of Rosetta, I should say on the surface of 67P, because what happens here as the comet gets closer and closer to the sun, the comet, of course, gets heated up. And of course, there are ices beneath the surface. These ices start to heat up. And when they start to heat up, they start to sublimate. And the gas pressures inside of the regolith material right here, or the general structure of the comet, get to the point where you get a blowout and you wind up getting this rubble that accumulates at the base of these cliffs. And we see this in a number of places along the surface of 67P here. And I'm not sure, but I think this cliff is located right next to the neck right here of this binary comet. So this is another example of a binary pair where the comet is actually two separate pieces that fused together billions of years ago, maybe out in the Kuiper belt, and has stayed together. And it's suspected it'll probably break apart eventually because there were fractures that were noticed right here. So just a little side note that I thought was just kind of fun to take a look at. So that concludes my presentation, and I thank you all for attending.
All right, ladies and gentlemen. Anybody have any questions? You are welcome to unmute and ask them if you would like to.
Well, thank you. Thank you very much, Kevin. Do we know the composition of Dimorphos? Is it, like a rubble pile or?
Well, we can't tell whether it's a rubble pile or a solid body, solid chunk of rock yet. We have to get close up into it to really see what it's made up of. These little tiny stellar occultations are only going to give us an idea of the relative size of these asteroids, and that's about it.
Okay.
I thought
Well,
for a moment I heard dinosaurs in the background.
Yeah. Chris, you'd say that this has been recorded. When you get a chance, can you send me, the link, the YouTube link, so I can distribute it?
Absolutely. Our guy will do a little tidying up at the tail and the end of it, and as soon as it's posted. But all of the previous CAS talks are also available on our YouTube channel. So if you want to go back and relive awesome moments.
Yeah, well, definitely. And Kevin, it sounds like there's going to be a lot of activity in the future as we get results, and you can look forward to us asking that you talk to us again.
Oh, I'd be happy to.
Yeah.
New information coming down at breakneck speed here. Can't keep up with it all.
Yeah, yeah. Well, I think this is at least the third asteroid presentation that you've given to us.
Yeah.
It's very interesting and significant.
Mm-hmm. It was fun putting it together.
I have a question. Kevin, thanks so much. This is Robert. Thanks so much for a great presentation. I'm not a scientist, but I think I followed a lot of what you said, and I really appreciate the clarity of the discussion. Is the ultimate goal here over the course of time, and I imagine we're talking in decades or hundreds of years, to have NASA create a fleet of some kind of defense against these potential inbound asteroids and so forth? Is that kind of where we're going over the course of time? Is that these are the first sort of ventures to try to figure out whether we can actually take action against these threats? Or
well, I don't know if NASA has planned that far ahead. They want to be able to have the ability to launch a spacecraft on a moment's notice if something like this does become a threat. And the design of this spacecraft was kind of dedicated towards that, I think. But other than that, right now we're just kind of feeling our way through and seeing what works and what doesn't work. So we're not really sure how effective this inertial redirection is going to be, but it may prove to be significant for these small asteroids that are more of a threat than the bigger ones.
Just for fun, Henry in the chat says, great planning by CAS, same day as Lucy launch. Thank you.
Yes.
Kevin.
Thanks,
you there?
Henry. Hi, Dan.
Yeah, hi. I remember some years back that the idea of preventing a collision with an asteroid would be best done by shepherding it, by, say, having a spacecraft loaded with water, enough water to be gravitationally effective, and getting it far enough out in space to just divert it slightly just a matter of a few arc minutes, gravitationally do it rather than try and break it apart. What happened to that idea?
I don't know. Haven't heard anything more on it. I think it's a really good idea. But we'd have to be able to intercept the asteroid at probably near or just before its aphelion in its orbit around the sun in order to make it effective. Because when you get it that far out, then you don't need much of a gravitational push to
No.
divert it just a little bit. The closer it
Right.
gets to Earth, the harder it is to divert. So you could possibly wind up doing two processes, one a gravitational diversion and one an impact diversion. And just to clarify, this impact with the DART mission is not big enough to break apart the asteroid. It's just enough to impart a change in the momentum of the asteroid, so it falls into a smaller orbit around its host asteroid.
Yeah, no mission to practice that particular technique is planned right now. Do you know of any?
No, not that I'm aware of.
Okay. Thanks, Kev.
You're welcome. Nice seeing you again.
Yeah, good to see you. Cheers. May the force be with you. Remember, I can say that.
Exactly.
Yeah, Dan, it is nice to see you. I was just going to comment that in the chat, Bob says, did anyone mention that Lucy spacecraft is carrying a diamond?
There might
I
be a
haven't
lot of
heard
them out
that.
there, who knows?
It is carrying gold, though.
Yeah.
But Kevin, as usual, a great talk, a fire hose of information, lots to think about. And it's amazing the number of missions that are launching what seems to be in rapid fire succession.
Mhm. Yeah, it's really kind of pleasing to see that after so many years of nothing happening.
Yeah.
Well, thanks, Chris, for setting all this up. Cernan sets up these Zoom meetings for us, so all we have to do is show up.
So thank goodness for technology, and it's been fun to be able to follow presentations from lots of places across the country. I know that Bob Kaplow at one point was, I think he still is, putting together a monthly list of interesting talks. And because of Zoom, you can now attend talks that are out on the West Coast and things like that. So
Right.
This might be a fortuitous side effect of this whole quarantine business.
yeah, to reach
Yeah.
way more people.
Yeah.
But great job
Well,
as usual, Kevin.
Thank you very
and
much.
Jim, we're always happy to have CAS. Anything we can do to help, let me know.
Well, you bet. Probably our next meeting will be in January, just as a heads up.
Okay.
I don't have a speaker yet, but I'm sure we'll come up with something good. And, see you all next time.
Hey,
And-
Jim, I just want to point out this, the next meeting will mark my 51st anniversary with the society.
Whoa,
Oh,
50
51 years, yeah.
50 years, huh? Well,
Wow.
we'll have to have a party or something.
Champagne.
Okay,
Yeah.
okay, that's quite an accomplishment, Dan. Jim, the other thing that I'd like to do is that if CAS is going to meet in person, that we get enough notice and I can confirm with the IT people here
Sure.
on campus so that we could actually also stream the meeting live if we wanted to.
Okay, well, what I think we'll probably continue with the Zoom presentations. I just have a real problem asking a speaker to give a talk wearing a mask. I'm sorry, I just, but we we would like to hold a board meeting at CERN sometime in the near future. And,
That would be good.
you know, we can, we can celebrate Dan's 50 years with CAS.
Wow.
But,
So Dan, when did you join CAS? When you were in diapers?
Actually, no, I was just about to turn 22 years old, in fact.
Oh, okay.
Yeah. When I joined, right.
my
And
God,
I joined when there was going to be a trip to the total solar eclipse, which went through Fort Stewart, Georgia. We actually had a field trip to it. And I got interested because of that. My younger brother pointed it out to me. He's sitting here in the room with me, in fact. And we went on that trip, and doggone, my last photograph of the sun was 1 minute and 45 seconds before the cloud out.
oh,
Oh, wow.
Yeah, before the totality was clouded out. Yeah, yeah, that was the last shot we got.
But you
That was-
got a shot.
Yeah, right. It was kind of sad. Just a sliver, little bit of a sun, and that was it. And then bang, it was gone. So, the cloud covered it. Yeah, that was kind of too bad. But I've seen 3 in the clear since, including the 1991 on the Baja, July of 91. That was, the sun was 80 degrees up, and totality was 6 minutes and 23 seconds.
Yep.
that's unusual.
Phenomenal.
Well, we'll have another opportunity in 2024, right?
That's
Yes.
correct. Yes.
April 8th.
Yep.
Get your
Well,
eclipse glasses here.
Or just a 4-hour trip to the totality track from
Yep.
here. So
Well,
it's-
thanks
it's not a
everybody
hard one.
for attending. I have to leave.
All right.
We'll see you at the next meeting.
Okay,
Nope.
Jim, take care.
Okay, thank you.
Bye, everybody.